Welcome to this tutorial on how to do least squares adjustment. Before we begin, there's a wonderful quote that Owl from Winnie the Pooh said. He said, "The only way to learn something is to do it." You should keep this in mind while moving forward. What is least square adjustment and why do we need it? Least squares is a method of adjustment that states that the sum of the squares of the observational residuals must be a minimum. A residual is simply the difference between the adjusted value and the measured value. This in essence means that the differential of the squares of residuals added is 0. In essence, the differential of the least squares criterion, as seen below there denoted by phi, is 0. The reason for this is that at a minimum, the gradient is 0 at that minimum point. Therefore, the differential will be 0. Why do we need it? Every measurement contains random errors caused by the environment, which cause each measurement to vary slightly. Because of this, an adjustment is done to give an estimate which fits the model exactly. Fits the model exactly means that these estimates will contain no error when inputted back into the model. This estimate is known as the adjusted value. Let's take the case of a distance. If a distance is measured 3 times to give 3 different solutions, an adjustment is needed to give one unique solution, as that distance cannot be 3 different values. This is the basis of adjustment. Adjustment can be done 2 ways: adjustment of indirect observations and adjustment of direct observations, or observations only. These 2 methods are known as the indirect method and the direct method of adjustment. Adjustment of indirect observations. If n0 is the minimum number of required elements to specify a mathematical model, then n is the number of measurements in excess of this minimum. For this method of least squares adjustment, n is also the number of condition equations, with n0 being the number of variables. To restate the distance example mentioned before, n0 would be 1, as there is only one variable, that is distance, and n would be 3, as it was measured 3 times. Examples of condition equations will be seen and talked about later on. Adjustment of direct observations. If R is the redundancy, or statistical degrees of freedom, as it is more commonly known, then R would be equal to n minus n0. For this method of least squares adjustment, R is now the number of condition equations, with n0 being the number of variables. So before, for indirect observations, n would be the number of condition equations, but for direct observations, R would be the number of condition equations. Consider this example. Figure Q1 to the bottom right depicts angles measured about a survey station. The observed values are alpha 1, 65 degrees, 0 minutes, 0 seconds, alpha 2, 65 degrees, 0 minutes, 30 seconds, alpha 3, 230 degrees, 0 minutes, 20 seconds, alpha 4, 130 degrees, 0 minutes, 25 seconds. All measurements are uncorrelated and have the same precision. Adjust the measured angles using least squares adjustment by the method of adjustment of indirect observations and adjustment of observations only, or adjustment of direct observations. To restate, the measured values are alpha 1, alpha 2, alpha 3, and alpha 4. Now, to arrive at an adjusted value, an adjustment must be added to the measurement. This is the basis of the condition equations. Alpha plus nu is equal to the adjusted value denoted by a hat, alpha hat in this instance. As depicted in the diagram, alpha 1, alpha 2, and alpha 3 are part of a circle. Therefore, alpha 3 can be written in terms of 360 minus alpha 1 plus alpha 2. Similarly, alpha 4 can be written in terms of alpha 1 plus alpha 2. Doing this gives 4 condition equations in terms of alpha 1 and alpha 2 only by solving for the adjustment of nu, seen in step 4 on the diagram in front of you. For step 5, as mentioned before, n0 is the number of variables our condition equations should contain, which is 2. And as we can see here, there are only 2 variables when substituted into the least square criterion. These 2 variables are alpha 1 hat and alpha 2 hat. Now, partially differentiating with respect to each variable and equating it to 0 gives n0 simultaneous equations. Seen by step 6, partially differentiating with respect to alpha 1 hat gives one equation, and partially differentiating with respect to alpha 2 hat gives another equation. When simultaneously solved, will yield a solution for alpha 1 hat and alpha 2 hat, the adjusted values of alpha 1 and alpha 2. Lastly, since the adjusted values for alpha 3 and alpha 4 were written in terms of alpha 1 hat and alpha 2 hat, they can be found. Your completed solution should have all the adjusted values as seen here. Method of adjustment performed before was adjustment of indirect observations. Here we will look at adjustment of observations only. To reiterate, n0 is 2, n is 4, and r would be 2. For this method of adjustment, there should be r condition equations. There should be 2 condition equations. The condition equations here would be alpha 1 hat plus alpha 2 hat plus alpha 3 hat is equal to 360 degrees, and alpha 1 hat plus alpha 2 hat is equal to alpha 4 hat. Keeping that in mind, nu 3 would become, as seen denoted by step 3, 360 minus alpha 3 minus alpha 1 hat minus alpha 2 hat, which when broken down further gives nu 3 to be minus 0 degrees 0 minutes 50 seconds minus nu 1 minus nu 2. And similarly, nu 4 becomes 0 degrees 0 minutes 5 seconds plus nu 1 plus nu 2. We now have nu 1, 2, 3, and 4 in terms of 1 and 2 only. There are 2 condition equations and 2 variables. Substituting into the least squares criterion results in an equation with only 2 variables, seen in step 5. Partially differentiating with respect to each variable and equating it to 0 gives 2 equations, which if simultaneously solved will give solutions for the adjustment, seen by step 6 and 7. Since the relationship between variables was determined earlier, all respective new values can be found, further allowing for all adjusted values to be found by measured value plus the respective adjustment. These questions have a logical flow to them when solving. We will look at that flow now. It is important to note that this flowchart and these solutions presented here are only applicable to measurements that are uncorrelated and of equal precision. These are the steps. Step 1. Understand and analyze the model. Step 2. State what n, n0, and r are. Step 3. Determine how elements relate to each other. Step 4. Create condition equations and solve for nu. Step 5. Substitute into the least square criterion. Step 6. Partially differentiate with respect to each variable and equate to 0. Step 7. Solve simultaneously. And with these solutions presented here, move on to step 8. Use the relation determined to solve for all elements. The relation determined from step 3. Step 9. Ensure adjusted values satisfy the model. Simply, looking at the example presented before, alpha 1 hat plus alpha 2 hat plus alpha 3 hat should equate to 360 degrees. Similarly, alpha 3 hat plus alpha 4 hat should also equate to 360 degrees.